class. Welcome to vectors. You made it through calculus, and now we're starting something completely new. So for those of you who have taken physics, today's lesson will be mostly a review, but that's kind of where it stops. So enjoy it while you can. So today we're going to learn what a vector actually is, define what a scalar is, what opposite vectors are and equal vectors, and also learn proper notation. So when we talk about the difference between a scalar and a vector, it's important to understand some examples to help further your understanding. So a scalar is something whose quantity, a quantity whose size, magnitude can be represented by just one number. So for example, age is a scalar quantity because you just have somebody's age, they're 17 or 30 or whatever. Volume is a scalar quantity. Area, speed is a scalar quantity. Temperature, things like that. But we're going to get into vectors, which are quantities that have both magnitude and direction. So for example, velocity. Velocity is speed with direction. So it is represented by a vector, okay, or something like friction. Okay, it has a magnitude, but it also has a direction. Okay, so a vector then has two elements to it. It has a length of the vector, which represents its magnitude, and then it has an arrow, which represents the direction, okay? And you'll see that this one is tilted in a certain way. So this is a vector, and we can call it vector AB. So we'll put an A here and a B here. We call this end the tail, and we call this end with the arrow the head. So tail to head. All right, so when we talk about this vector, we can call it vector AB with capitals, and then we put a little half arrow above it. So AB is a vector. Now, we always label vectors with the tail letter first and the head letter second. So this means like from A to B is the direction that it's going. Okay, if we talk about its magnitude, we would put absolute value signs around the vector. So this is its magnitude. Okay, and something else to consider about magnitude is that it's always non-negative. Okay, always non-negative. So that means it can be 0. Or a positive number. Okay, you cannot have a negative magnitude. Okay, so how this could be seen within a context, let's say here that 1 centimeter equals 100 kilometers per hour. So if you measure this, it should be 4 centimeters long if it printed correctly. So you could say that vector AB can represent velocity of a plane. Okay, and so because it is 4 centimeters long, it would be going 400 kilometers per hour and then northeast due to the direction since it's going northeast. So that's what this vector could represent. Okay. Now, opposite vectors are two vectors that have the same magnitude but point in opposite directions. Okay, so we could call this vector A, B, okay, and we can call this the same one. Here's B and A. So notationally, we can say, that vector AB is equal to negative vector BA. So we can say that AB is equal to negative BA, okay? This is BA. But the magnitude of AB is equal to the magnitude of BA. Okay. Vectors can also be represented with lowercase letters. So I could call this vector v, the whole thing, and then this vector would be negative v in relation. So v, the magnitude of vector v is equal to the magnitude of negative v, okay? But vector v and negative vector v point in opposite directions. So that's just a definition for you. So basically, they cancel each other out if you want to think about it that way. So you're going like upstream and then downstream again, or whatever. You get back to start. So vectors can be represented on a coordinate plane. So up here, these are called geometric vectors. They're kind of just drawn in space without reference to the coordinate plane. But vectors can be represented on the coordinate plane. These are called algebraic vectors, okay? So for example, if we have vector A being 2, 0, so let's just say this is 1 and this is 2. So I can take a different color here and draw the vector 2, 0. And this would be vector A. Okay, so A, 2, 0 is a vector having its tail at the origin and its head at 2, 0. This vector has a magnitude of 2, okay, because it's right along there. Okay, describe and draw negative A, assuming its tail is also at the origin. So this vector would go in the opposite direction, but it would be at the same length. So we would say that negative A is equal to negative 2, 0. Okay, so it would terminate at negative 2, 0. So it's the same magnitude, but going in the opposite direction. Okay, so now we get to equal or equivalent vectors. So two vectors, A, B, and C, D, are equal if and only if, okay, we have to meet two criteria here. So the first criteria is that AB and CD are parallel and in the same direction. Okay, so that is the first criteria. And the second criteria is that the magnitude of AB is equal to the magnitude of CD. So we can describe this as AB and CD. So essentially, it's the same vector, just translated or moved around anywhere else. So note, these vectors can be translated to be coincident with each other. So coincident means one on top of each other. So I could technically grab this vector and move it around so that it would lie perfectly on top of the other vector. And that's one way to tell if vectors are equal. Okay, so we have to label this diagram first. So this is A, B, C, D, and this point in here is E. Okay, ABCD is a rhombus drawn with its two diagonals. Name equal vectors. So because it is a rhombus, that means that side lengths are all equal. So the magnitude of all these side lengths is equal, but we have to look at the direction of the vectors in order to talk about it properly. So we can say that AB, vector AB, is equal to vector DC. So notice that I'm labeling it from tail to head, okay? And that AB and DC go in the same direction. So those two are equal vectors. Okay, what about DA? What is its equal vector? Take a look. Okay, it would be CB. So again, it's the same magnitude because it's a rhombus, and it's the same direction because rhombuses. Anyway, they're parallel. Sides are parallel. Okay, we can also say that AE is equal to EC because we know the diagonals of rhombus bisect each other. And with that logic, we can see that DE would be equal to EB. Now note, if we wanted to talk about opposite vectors, we could say that AB is opposite to CD. So CD would be a vector that is from C to D, like that would be CD. So notationally, just so you guys know, if you write CD, that's the same thing as writing negative DC. So when you see a negative in front of two letters representing a vector, one way to rewrite that is to just take the negative away and flip, because you're flipping from tail to head. So this means from C to D. This means from D to C, but then go the opposite way, which means going from C to D. Okay? So in our discussion thus far, we have illustrated our ideas with geometric vectors. Geometric vectors are those without reference to the Cartesian plane, as I mentioned. The ability to use vectors in applications usually requires us to place them on a coordinate plane, and those are algebraic vectors. So that was, again, seen in example 1. Okay, so check out the success criteria. Make sure you can do this, and hopefully your work with this will help solidify these concepts. Thanks for watching, guys. Hope you learned lots.